So with the roller coaster loops and bucket of water problems, first I want you to try this demonstration where you get a bucket, put a little bit of water in it, and swing it over your head in a circle. And I want you to feel when you go as slow as possible at the top, you hopefully will feel no force that you need to pull down with. If you go fast, you should be able to feel the bucket pulling out on your arm as your arm pulls the bucket towards the center. And if you don't have a bucket of water, you can try a plastic shopping bag and just put a couple unbreakable things in it to swing around your head. So in this example, I want to look at what the force diagrams would look like for the minimum velocity at the top, if you're going fast at the top, and at the bottom. So if I have my minimum velocity at the top up here, this is going to be when I don't need to pull it towards the center of the circle. Because remember that your acceleration to go in a circle is always towards the center of the circle. And I'm going to have gravitational force on my side here. So I'm going to have my gravitational force pulling me towards the center of the circle. If you go faster than that, then you need more force to pull it in. So not only am I going to have the same gravitational force, but I will also have a tension pulling it in. And lastly, for the bottom, I'm going to still have gravitational force pulling it down. But now I'm going to have to pull the bucket up, otherwise it'll fall on the ground. Now let's talk about net force equations. So for the first one, for your minimum velocity, the sum of my forces in the x direction is just going to be my gravitational force. And that'll be equal to my mass times the acceleration. And specifically, this will be the acceleration to go in a circle. So in this case, it'll be helpful if I make downwards my positive direction because my acceleration is towards the center of the circle. So that way, both my gravitational force and my acceleration are positive numbers. If I had it the other way, if I wanted to do minus Fg, then I would need to do mass times a negative acceleration towards the center of the circle. So either way works. My recommendation is wherever the center of your circle is, make that your positive direction. So for the second one, I'm going to do the same thing. I'm going to do some of my forces in the y direction, which is just my gravitational force and my tension. Again, I'm going to have towards the center of the circle as my positive direction. So that way I can have mass times a positive acceleration. And lastly, at the bottom, I need to have my object accelerating still towards the center of the circle, but that's going to be up now. So that's the sum of my forces in the y direction is going to be my tension minus my gravitational force is equal to mass times acceleration to go in a circle. So now I have the positive direction upwards because I want to make sure that my accelerating direction or the center of the circle is in the positive direction. So the question asks, the bucket makes a circle with a radius of 0.6 meters. How fast does the bucket need to go to be going at the top so you do not get wet? So that is going to be this first example here. So for the one at the top, the only force that I have is my gravitational force. And I'm going to remember that gravitational force is equal to mass times my gravitational field strength. And that's going to be equal to my mass times the acceleration to go in a circle, which is v squared over r. The first thing I notice here is that I have mass on both sides. So I'm going to divide both sides by mass. And then I'm going to end up with g is equal to v squared over r. And the radius that we were given in this example was 0.6. So g, which is 9.8, is equal to v squared over 0.6. I'll multiply both sides by 0.6. So 0.6 times 9.8 is 5.88, and that's equal to v squared. So then all I need to do is square root both sides, and I get a velocity of 2.42. So the second part of this says, if you go the same speed at the bottom, how much force do you need to apply to the 3 kilogram bucket? So for this one, I'm going to remember what we talked about before, that at the bottom, my gravitational force is going down and my tension is going up. Because I need to accelerate towards the center of the circle, my tension must be bigger than my gravitational force. And I'm going to remember that gravitational force is equal to m times g, and acceleration to go in a circle is v squared over r. So now I'm going to solve for tension. So my tension minus mg is equal to my mass times v squared over r. And because I am solving for tension, I can go ahead and move my mg to both sides. And I want to warn you that the most common mistake here is that students will get to this point and divide everything by m, because they forget that this ft does not have an m attached to it. So you actually cannot cancel m out in this case. So I add the mg to both sides and I get my tension is equal to mass times v squared over r plus mg. So I just need to plug in those numbers. So when I plug in the numbers, I have 3 times my velocity squared, which we just found was 2.42, divided by the radius, which was 0.6, and then plus mg, where my mass was 3 and g is 9.8. I plug that into my calculator and I get 29.28 plus 29.4, and I get a tension force of 58.7 newtons.